Okay, normalize. Whoop, no, we need some screen. Normalization, right. So normalization is about data redundancy, which is basically duplication of data. And duplication can happen in, well, I've identified 2 ways. There may actually be more ways. But you can have duplication across rows in a table. So effectively, you've got duplication of information in different rows in a table. Or you can have duplication in rows across tables. So the duplication may be across tables. So duplication can occur within tables or across tables. It wastes space. And as I said this morning, you want to reduce spacage, get everything down as small as possible, as fast as possible, as efficient as possible. But it not only wastes space, it leads to problems in maintaining data integrity. So if you've got duplication of data across down rows or in different tables, you must keep all these copies of the data in sync together. Otherwise, we get, well, not redundancy, but we get inconsistency between those data values, which should be the same. And it prevents normalization, prevents what are called database anomalies occurring in your design. So one is to reduce duplication, and the other is to prevent database design anomalies. So database design anomalies first. And again, these are, I don't know, they're a bit sort of comic book sort of examples, but they still illustrate the problem. And there are 3 types of database anomalies, and these result from poorly designed database. So here's a table, employee skills, which has an employee ID, an address, and a skill. So 3 fields. If the address changes and an employee has multiple skills, then more than one row must be updated because there's one row for each employee and their skill. It's also this table is also storing their address, so the address is duplicated. So if you've got more than one skill, we've got to duplicate the address information. So that's called an update anomaly. An update anomaly occurs if not all rows are updated. So if this person had more than one skill, so they were an electrician and a plumber and a forklift truck driver, there would be 3 rows, 3 copies of the address. If they move address, all 3 rows with the address need to be updated. So that's called an update anomaly. Insertion anomalies. So we've got a table, faculty ID, name, hire date, module code. So this is to do with data insertion. So data cannot be inserted. An insertion anomaly occurs where data cannot be inserted without the presence of other data. But that insertion is not reliant on that other data being present. So all faculty must teach on at least one module. A new faculty has been hired but not allocated to a module. If module code is required, then we couldn't enter a new faculty member in until we've got a module, until they have a module assigned to them. So module code in this case is obligatory. And that is what's called an insertion data because we want to insert a new faculty member, a name, hire date, but we can't do it because there's a constraint on the module code. And these are all the results of incorrectly designed databases because they haven't been properly normalized. Final one is called a deletion anomaly, which is the opposite of an insertion anomaly. So we've got the same table, faculty, name, hire date, module code. Faculty member on sabbatical does not teach modules, so we must delete the record. So To delete the module code from the person's record means we have to delete the whole record and we lose our faculty member. So these are the kinds of things that normalization are trying to avoid, as well as duplication. So normalization is a gradual reduction of repetitions, redundancies in tables, in one or more tables, mostly in one table, through the creation of several increasingly efficient compact relations or tables to what's called a normalization form, and there's several different normalization forms. It results in efficient data insertion, deletion, and modification, and minimizes redesign costs because you've got your data organized in a sensible fashion. Therefore, if you need to redesign the system, hopefully it results in minimum redesign effort. So as I say, it breaks big table into smaller linked tables. COD defined 3. Remember COD, grandfather of the relational database system. 3 forms: first NF, second normal form, and third normal form. There's the definitions there: fields containing single unrepeated values, etc., etc. We'll see each one of those in sequence. Since COD, there have been a whole sequence of other normal forms defined. Well, we've got 3NF there, so that should be 4NF, 5NF, 6NF, EKNF. Don't ask me what those are, they're well beyond me. But there are these, so for hardcore database administrators, you can go beyond 3NF normal form into further normalization. I would say for most everyday databases, 3NF is good. Everything else is pretty, some of it's almost theoretical, and some of it is for maybe have benefits for large corporate database systems. We're only going for 3 normal forms. Okay, the first normal form. First normal form is where each field contains a single unrepeated value. So, here's an example. All right. Well, there's 2 different types actually I've got here. One is that where you have different types of information in the field, in the single field. The other one is where you have the same type of information in the field. And these result in different normalization approaches. So here's an example, very simple example of names. We've got one field in our initial table with name as an attribute. So in our logical design, we had an attribute name. Now, and that name field might be John Henry, Abigail, Joseph, Winsome, whatever, 3 names, 2 names. That's very straightforward. These are actually different. We can regard these, while they're all names, they are distinct elements of a name. So we have a first name, we have a middle name, and we have a surname. So we can break apart that name, full name, into subparts. So we can have a first name field, a middle name field, and a surname field. Very straightforward. So from one field, we break it apart into 3 different fields. The other situation is where each field contains a single unrepeated value of the same type of information. So this is a slightly different situation in our solution. So here's our initial table. It's a module, it's believed to be a module table. So it's got a module code, it's got a course, and then we have, a list of students. Now, of course, this is not a single unrepeated value. This is more than one repeated value. Students is a list. It's not an individual value. So this table, well, initially we thought this was about modules. After all, Peter Brown and Jenny Wong are taking this module. It's got to be a module. Isn't it a table about modules? Well, no. It's actually information about students, and the modularity of it is, in fact, an attribute of a student. So in an original design, the student was an attribute of the module. In fact, to a certain extent, it's better to represent it the module being an attribute of a student. So what we need to do is basically we need to get rid of these repetitions, and because they're the same values, they end up going in the same field. We don't need new fields with different names because these are the same information. So in this case, what we do is instead of having a table called modules, we have to convert it into a table called students, and we have one row for each of the students. So we now, and the module code, which we originally thought was our primary field for our module table, becomes an attribute of the student table. Is that clear? Yep. Yep, it's relatively straightforward. We've got more than one student. Each student should have the unknown row. That's what we want. That's first normal form. Very straightforward. Second normal form, this is where it gets a little bit more complicated. All fields must be exclusively dependent on the key fields. If we've got a table of supplier and parts, got a supplier status field, which is actually which, it's kind of the, whether it's in the EU zone or the United Kingdom zone, rather, I think a bit out of date. It doesn't really matter. We've got a city, the city where the supplier is, and effectively what sort of economic zone they're in. We've got a part number, and we've got a quantity of parts ordered from the supplier. Now, city is a non-key field. It's not part of the key. The primary key is supplier ID and part number in this table. It's a composite key of the supplier and the parts. So city is a non-key field and is dependent on only of the one of the fields defining the primary key. So city is dependent on where the supplier is. It's not dependent on what the part number. So this is not in second normal form because we've got a non-key field that is dependent on only part of the primary key of the table. This relation is not in second normal form. So to convert this into second normal form, what we need to do is replace the relation of the table with two new relations. So in which every non-key field is now irreducibly dependent on the primary key field in those tables. So we can break apart. We have a supplier table now. So we break our original table apart into two tables, one called supplier and one called order or something like that. We haven't actually given it a name. It's called two, which is a lousy name. So one called supplier and one called order. So in this case, now city is only dependent on the supplier. So that's great. We're dependent just on the only primary key in this table. The primary key has one field, supplier number, and the city is dependent on the supplier number. That's great. We are now in the situation where all non-key fields are now irreducibly dependent on a single primary, on the primary key. We can also look at the second table here. It's not in this case, quantity is dependent both on the supplier and the part number, so that's good. So if the quantity is irreducibly an order, you have to order the parts from a supplier. So these are irreducibly dependent on the two composite primary key here. City and status are irreducibly dependent on the single primary key field supplier number in there. Great, second normal form, done. Third normal form. If a table is in second normal form or a table is in third normal form, if it is in second normal form and all non-keyed fields are mutually independent of one another. So, here's our supplier table, supplier number, status, city. This table is not in third normal form because status, the economic zone, is dependent on city and both are non-key fields. Yeah? So London is always within the UK economic zone. Paris is always within the EU economic zone. So therefore, these are not independent of each other. Solution is to split, again, is to split that one table into two tables. So we now have a supplier table with a supplier and a city ID. And then we have a city table with the city and its status. So now city and status are both dependent on the city number. And the city number is fine here. So this is now in third normal form. City status is dependent on city number. In supplier, what's this? And in supplier is different, sorry. In third normal form, the city status is dependent on the key field city number, while city number in supplier is dependent on the field supplier. Yeah, that's correct. That's normalization for you. And of course, this afternoon we're going to have a normalization exercise like last week, split into groups, maybe slightly, and we'll have a normalization exercise. So I'm going to give you a table and you're going to normalize it. But the reality is that many relational databases are not fully normalized, or even to third normal form here. Why? Because normalization is about maintaining data integrity, also improving speed as a result, but the primary function of normalization is to prevent data redundancy duplication. That's its primary function. So it's really important where data is being entered, updated on a regular basis, because that's where integrity problems. If your database is stable, you're not going to have these update anomalies, these problems with these anomalies with updating and changing the data. So it's really important for transaction processing. And what I mean is transaction processing is situations like online retailers. Anywhere where you've got large amounts of data being input at any particular time, transactions being done, you want to make sure you put in the right address information because the book delivered, that's being ordered from Amazon has to arrive in the right place. So data integrity is really important under these kind of transaction situations. So that's one reason why normalization is important, where you've got to maintain the data integrity because you've got lots of data being entered, updated, etc. But the other reason databases are not normalized is simply people. People are lazy and or ignorant. And, they're built by people without training. So simply people who don't know about the process of building databases. I've worked with a lot of biologists over the years, and they don't have, increasingly they do have a tradition of trying it, but you don't get taught relational database design as a biologist. But you might end up in a job where you have to collate and create databases, so you become a database designer by default because of there's nobody else there to do it, therefore you're given it, and that's what you do. To a certain extent, that's how I learned to program. I had a job where I had a job that required programming, so I learned how to program. So it's built by people without training, or they simply don't need to worry about normalization. Perhaps it's a small application. Perhaps there are only a couple of users. Perhaps the time and investment in normalizing the data set just isn't worth it, as far as they're concerned. So there are issues, sort of people issues, for why databases aren't designed well. But many systems, let's say, so maintaining integrity is important for transaction processes, but if you're not undertaking transactions, if you've effectively got a static database that's being used in a read-only fashion, maintaining integrity is not an issue. Not simply because you're not updating the data. So therefore, maintaining those integrity constraints are not so important. Integrity of the data itself may be still very important, but because it's not changing, as long as your data has integrity to start with, it's not going to lose that integrity through time. There are design costs, as I say, in normalization. Things to decide which take time, like is an address, I mentioned this last week, is an address one field or many? These are design decisions. They take time to think about and implement. So there's a sort of cost behind, there is a cost behind these things. There's a design cost. There's also an efficiency cost. Normalization, breaking the tables apart into smaller and smaller tables, but with tighter and tighter relationships between them, is great for maintaining integrity. But every time you have to do a join in a relational database, that's costing processing time. That involves processing time. So, for example, queries may be much more efficient where they don't have to undertake the joins required, all the joins required if your database is normalized. Okay, remember we were breaking apart these tables into smaller tables which would have to be joined together to return a result from a query. The more joins we have to make, the slower the query is. And if query speed is important, therefore undertaking all these joins may not be the best way of doing it. We may better have a denormalized database system that allows us to maximize our query performance. And this is what happens in data mining situations. So I think we're going to have a lecture maybe sometime just before Christmas on data mining. We'll go into this kind of stuff in a bit more detail. Oh dear, what's happening here? Right. Okay, so in a lot of data mining situations, what they use is a denormalized schema called a star schema. So we'll have a whole lecture, well, not a whole lecture on data, but we'll revisit this later in the thing. So in this case, in a star schema, what you have is a central table which stores the dimension or the object that you're interested in investigating. Data mining is just the process of exploring large data sets. And as I say, we'll go into that in more detail. So rather than have a fully normalized form, what you have is a central table, which is the thing that you're trying to understand, customer sales, whatever it might be. I think it's a customer sales example, products. So we've got the base information, what was sold to whom, or if this is about customer calls about something, maybe it's a call, you know, what do you call it, a call center or whatever. And they're interested in what customers called, what product they were calling about, the time that they called, days of the week, quarters, months, years, and which staff identified it. So those are the dimensions that they want to explore, and they want to explore how long the calls took, how much time the staff used, for example, in dealing with a query on those dimensions. So rather than work with the transaction, this could be Amazon or something like that, a company like that, it may be dealing with a database like this. So instead of having in the ordering system where people are actually making orders and things like that, they maybe have a fully normalized system to maintain data integrity because of the constant updating. However, if they're mining the information that's already been recorded from the call center, that's no longer being changed and updated on a daily basis. They've basically done a data dump. So they've got a sort of static data set. Then they may well denormalize it to maximize the speed of exploring through the data set. So this is just an example of where denormalization is done on a regular basis in data mining situations. Of course, the standard way to increase, before you go into denormalization approaches, the standard thing to do would be to add indexes to your database to increase performance. Again, this is just one slide on indexes. We've met them before, just to show that they speed up access stored in database. Postgres supports lots of different types of indexes which are applied to different types of data sets. We're not going to go into any great detail just to see that there's alternative choices of indexes. B-trees, I think we met really briefly, good for range queries between, queries between X and Y values, those kind of range queries. Hash index is only good for equality of queries where continent equals this, that kind of queries. Other more complex indexes, such as GIN, generalized inverted indexes, are good for one-to-n relationships. Full text searches where you've got sort of whole books stored, so large amounts of text stored in particular fields. And GIST and SPGIST indexes, which are multi-algorithmic ones. Basically, that this type of index will choose what type of indexing system is applied depending on the characteristics of the data in the data set. And these are really good for, well, you almost always set a GIST index on a spatial data column. And when we get back after the reading week, we're going to get into the space, of course. We're going to start adding the spatial component into the relational databases, and we'll meet GIST indexes then. Just one thing to say about our indexes: highly flexible in advanced database systems. So the administrator can set indexes to be used for general use. So for somebody who's just writing a number of queries for general, so ad hoc queries. So for general usage to try and maximize overall performance of the whole database. But you can also use indexes optimized for particular types of queries. So if you're constantly doing one type of query, for example, finding fast food restaurants within 1 mile of my house. If you're constantly doing that kind of distance query, then you can optimize your query so that the index, you can index on the distance value, and you can undertake much quicker distance queries. So you can tailor your indexes to the queries to maximize query performance, or for more general ad hoc usage. Okay, the final thing that I thought I'd mention in this sort of moving from a logical to a physical model is data standards. Now, data standards is, to me, something that is not really integrated into entity relationship modeling in any way, or into indeed to a certain extent the conceptual design or the logical design component. It's something that's sort of arrived after the relational model was actually designed, came about in the first place, and the ER diagram system was developed by Chen in the 70s. Standards are really important nowadays, especially with data being distributed across the World Wide Web, open data. It's really important. Data standards have become really important. We'll meet them again throughout the module. And I was wondering actually last night as I lay in bed, as you do before you go to sleep, I suddenly thought, well, where do data standards come into the design process, the data modeling process? Because they clearly should do, and yet they're nowhere in the conceptual modeling. You read the books, there's nothing in conceptual modeling, nothing in logical modeling, and nothing in physical modeling particularly about it. It's the context in which you're working. So I'm not quite sure where it actually comes in, but you should actually consider it right from the beginning, I think, from the conceptual level, certainly from the logical level onwards. So as we know, standards are just agreed, standardized ways of doing things. And what you do as a database designer, you need to consider or identify what standards operate in or intersect with your problem domain. Okay, so you need to. So an organisation, a water company or an environment agency may have a standard set of ways of doing things. We store metadata in a particular standard format. For example, the EC European Community Inspire infrastructure for spatial information in the European community is a metadata standard for spatial data across the European Union, so that allows European level data, metadata holdings to be collated. So, for example, if you're working for the British Environmental Agency, you might be interested in you might have to pass data information to the European Commission, so therefore you need to make sure your database is compliant with the EC Inspire standards. You also may need to pass data to the UK government, so you have to make sure that you meet the UK government metadata standards, and those differ slightly from the European level standards. Okay, so we're going to hit the standards, metadata standards and things a great deal later on. But when you're building your database, certainly at the logical physical design stage, consider what standards may operate within your organisation or be relevant to your organisation. There may also be internal ad hoc standards that are nothing to do with specified international standards. It's just the way IBM do things. It's the way Westminster County Council have decided to do things. And then so those are the things that are operating in your environment at the moment. And then there's the things that are outside that maybe you should incorporate into your environment as well. So, for example, we discussed this briefly last week. The Royal Mail postal address file is the list of postcodes and addresses for the United Kingdom maintained by the Royal Mail. That provides a de facto standard for UK addresses. It is not agreed by any standards organisation. It is not an ISO standard. It's how the Royal Mail treats addresses, and everybody with any common sense in the UK deals with addresses in the same way as the Royal Mail deals with addresses, because they might buy the Royal Address post file. You may need to collate information with other data sets which are georeferenced by postcode file. Always a good idea. So if you've got addresses in your system, consider the Royal Mail standard. So think about any other situations in your data set where standards may exist, and they may be official standards, agreed standards, or they may be more ad hoc organisational level standards, which still may be worth thinking about. And one of the costs, and this is why I thought about it last night, is that if you're following standards, you may end up with extra fields in your database with absolutely no data in, because half the fields in the postal address file are not relevant to your implementation. Maybe you're only using 20 out of the 50, 60 fields defined by Inspire. So that's going to result in a poor database design. From a database design perspective, from the sort of physical database design perspective, you've got fields with no data in, for example. But it has the benefit that you are following a standardized, and therefore your data should hopefully be what we call interoperable with other data sets, because you're following a standard. Oh, well, there we go. Just one last little thing. Here's the postcode. So I went to the Royal Mail website at 8:30 this morning, and this is what the PAF file, how the Royal Mail states the postal address file fields are. So you've got an organisation name. They just tell you what it's a text and how many characters it is. So it's not, it's just a simple, relatively basic, sort of logical level map. Importantly, is that this definition, this is not just the definition. This is just the table telling us what data type it is. And it's really important, and I perhaps didn't emphasise this enough with the logical modelling last week, is that you actually clearly define what these fields actually are as well. This is really, really important, and I probably didn't emphasise this enough last week. So associated with that table is a definition, a clear and hopefully reasonably unambiguous definition of what those actual fields are and what can go in those fields. So in this case, And to a certain extent, it's got the history as well, any changes between the formats as well. So here we've got a definition of a locality. What is a locality and what actually is a postcode? What are the values? Postcode type has S for small, it's got a restricted number of valid entries. So consider standards. Standards may result in a slightly bloated database design, but one that is compliant with standards and therefore hopefully or should enables data sets with a similar which implement a similar standard to be brought together.